Hello?
Okay, hello everyone. First of all, this is my honor to be here and talk about my presentation today. My name is Khoi-Nguyen, and my presentation today is auto curation of sports highlights for Wimbledon and US Open in 2017. This is the work I did at IBM Research Center together with my team last year for my summer internship. Imagine that you watch a video of sports. It takes hours of footage, and you want to see only the interesting one, the interesting snippet of the whole video. So what do? You look at the highlights videos. So the objective of the system here is to produce from 1 to 2 minutes of highlights videos of various segments of footage for two tournaments, which are Wimbledon and US Open in 2017. So I would like to emphasize that in 2017, this is the official highlight videos created by Watson IBM. There was a company that created highlights before, but in the past, but Watson replaced that company last year and become the official highlight creator. And here is the screenshot of the dashboard created by our system deploying on US Open 2017. There was another one in Wimbledon, but I only show one tournament over here. The work has already generated a lot of interest and media coverage and has brought back tremendous success. And as you can see here, there are some articles mentioned about our system last year. So this is the team that built the team. This is the collaboration work between IBM Watson Research Center and IBM iX sport team. So the main contribution of the system is that this is the first of a kind system for automatically that can extract the tennis highlights. And we introduced a novel technique for learning multimodal classifiers. And the classifier can cascade along different frameworks for players' celebration recognition. And we also have a live demonstration of the system at the credit tennis tournaments. So as you can see that for both tournaments, there are hundreds and hundreds of tennis players that joining each year. And the tournaments last from 13 to 20 days. And on our busy days, the matches can occupy up to like 20 different courts. So this results in hundreds of hours of footage, and we have to process them all. This is one of the biggest challenge of the system. We have to return the highlights quickly for simultaneous matches, and therefore we can only extract the frames and look at the frames at a really high frequency, low frequency, which are only 1 frame per second. So this is the main challenge of the system. And in this picture, you can see that this is the main architecture of the entire system. It involves multiple modules that process all of the metadata, both visual and audio information. So in the left-hand side, you have a lot of sensors to collect a wide variety of data, such as where are the bones, the position of the bones, and where are the players. And we also have statisticians to record things like who wins and by how many points, etc. And they are comprehensively used to screen the data out to provide potential candidates for our system to work. However, within that kind of candidates, it also have a lot of noise, and we have a lot of trouble to process them. I'm going to talk about the challenge on the visual and audio challenge later. So in the talk here, we mainly focus on the ranking system. In the presentation, it actually scores the candidate videos based on the visual and audio information. For example, it recognized the crowd cheering sound and the celebration action from the players. We also use Watson Visual Recognition's API to detect handshakes. So if you actually go to our website and see the highlights videos, all of the highlight videos has to be ended with the handshake between players. This is one of the business rules we have to follow to create the highlights. So after that, everything is combined together with the constraints of business rules I've just mentioned. This is only one of the business rules. And everything is combined to encode the structures of the video and build the final highlights video. So what is the problem statement? the problem statement is that given a short video clip, a short snippet, how do we detect and score the level of excitement from of the players? So since one type of data is not enough, doesn't provide us enough information and accuracy, we decided to combine the information from both audio and visual cues. They corresponding to the player, for example, the visual cues corresponding to the player celebration action, and the audio corresponds to the crowd cheering from the audience. And besides, those kinds of information are available in all the video clips, so it's really easily extracted to create for the input of our system. And so first of all, for the audio cues, which is the crowd cheering recognition. So we explore the deep models to represent audio data. Specifically, we adopt the SoundNet from MIT. This is a CNN that was trained on 2 million videos with environmental sounds. We use the model to create a high-dimensional vector to represent the audio itself. And this is actually a legacy system for a previous system, which is the Golf Masters. And that system was deployed for the golf tournament earlier last year in April. And this system was used for the crowd cheering recognition, and it was proved to be effective. And since the sound cheering in golf and tennis are kind of similar, so we reuse the system in the tennis system. So the next thing is, how do we deal with the visual information, which is the action recognition? So what we want to do is to identify a player's celebration after a good shot. So to do it, we adopt the residual net architecture, and we use the way that was pre-trained on our previous model in golf tournament, and to initialize the training process. Actually, we also have to do multiple rounds of bootstrapping, and we also refine the action recognition results with the facial expression, which is going to be explained in the later slides. So if you look at the right-hand side, you can see that the variety of training samples, we have a lot of visual variety, and which is also one of the challenges of the system we have to deal with. So here are the challenges that we tackled. So different from golf, the celebration action in tennis is really confusing. For example, in golf, most of the time the players has this kind of gesture, and when they celebrate, the celebration action is really distinctive, like this. So, but in tennis, when we have then the players are celebrating, the action can be like this, which is really distinctive, but it can also be like this. And when the players doing like this, it's really we can confuse this with the action when they trying to hold the ball and serve the ball, which is over there. And in tennis, players don't tend to celebrate with a high level of excitement throughout the match, so the actions are pretty subtle and it's really hard to recognize. And however, this is more recognizable towards the end of a match. We also have some confusion due to the background noise from the audience and or unexpected celebration action. So as you can see here, this is one of the celebrations that we can see in the real match. So the player is lying down to celebrate, and this is really unexpected, and we cannot see it like most of the time in the training data set. And talking about the training data set, this is another problem because we have no crowd truth training data. So, and there, the training data, so when you look at a tennis video, most of the time we don't have the celebration action, so it's really hard to extract the celebration for training. And as I mentioned before, the speed of the system is one of the biggest challenge because we have to return the results in real time, and therefore we can only afford to extract the images at 1 frame per second. So another visual information that we can use is the facial expressions of the players. So we observed that the player's expression is also a very valuable source of information, as you can see over here. Therefore, we can use this kind of information to increase or reduce the score, the celebration action score, according to the player's level of excitement, the facial excitement. So we use the SSD framework to detect the body parts and extract only the face. And we applied SSD on the training data to annotate the face and then fine-tune a new model using VGG faces. So we observed that the expression of tennis players can be split into 4 distinctive classes, which are named as aggressive, tense, smiling, and neutral. And therefore, we annotate the data following this manner to train a new model. So this is how we aggregate and combine the action and facial expression. So let X be the video clips with multiple frames XT, and we feed them on to our 2 classifier models at action and facial expression. Each frame XT will give a score YT, and this is the individual frame scores. Therefore, we have an array of frames scored YT corresponding to a whole video clip, and each array of YT is fed into aggregation modules and to create a score ZT, ZZ, which corresponds to the whole video. And we have another action refining to combine the emotion score with the action score to have the final refined action score. So this is what the results of combining the facial expression with the celebration action. In this example, so in this one, we have the whole video, and we extracted the frames in 1 frame per second. So we have a short snippet of 9 frames in total. And the facial expression give us the score of 1.0 for aggressive. So in this one, you can see that the all action score is just around 0.668, which is really low. But it actually it has to have higher score because the player is actually celebrating. The problem can be seen from the fact that the camera from the sixth frame, the whole body of the player is not visible. And in this one, especially in this one, we only see the face, not the hands. So it's really hard for the actions classifier to recognize this as a celebration action. But if we look at the 3 frames, we can see that the facial expression of the player is really visible. So we can use that to refine action, and actually the refined action, the action was refined and improved from 0.6 to 0.9, which is much better. Therefore, we can conclude that the emotion can improve the action score. So another example, so in these examples, the all action score is really high, which shouldn't be, because this is not really a celebration action sample. And however, when we look at the emotion score, this is really high toward a neutral score, which is around 0.9. So using this one, the action score is refined to be 0.75, which is much better. So therefore, it means that the emotion score can suppress the non-action score. This is another example. So the all action score is 1.0, which is really good, and we want to retain this kind of results. But however, in our emotion score is high toward the neutral score. However, the confidence of the score is not really high. Therefore, the action score is refined and it will reduce, but not really significantly. Therefore, action score is not heavily affected when the emotion score doesn't have very high confidence. So this is the quantitative results of our system. This is the RC curves. For the Wimbledon tournament, we have the cheering, action, and expression RC, which are respectively 95%, 89, and 83. And the same thing, we have a similar thing for the US Open tournament, which are 93, 94, and 75. So because we're talking about how the user experiments, we want users to have the good experiments using our system. Therefore, we also have the human evaluations of our system. And we use Amazon Mechanical Turk to survey the human evaluations of the system. So the upper figures is the user preference, and the lower score ones are the user reasoning why they choose, why they have that reasoning preference. So the red lines are the user experience saying that the non-H5 is better than H5. By the way, H5 is the name of our system. The blue lines is the idea when H5 is better than non-H5, and the gray lines are when they are equivalent. And we can see that the growth of the gray curves, which represents the indecisions of the users, which moving from 8 to 15 users. And the reason of the choice is highly skewed toward how exciting the clip was, as you can see in the lower figures. So as users pay less attention to the clip clarity and player scoring or significance of the point pointed again, it means that our assumption to score a video based on the exciting level is the good assumption. So to conclude my talk, we have built a robot system that can detect and score the level of excitement in a video clip. We have deployed and produced official highlights for Wimbledon and US Open in 2017 last year, and we have already generated a lot of interest and media coverage. If you are interested, you can go to these links to check out the dashboard and the video highlights. Thank you for listening.
Thank you so much. This was very interesting. Any questions?
Yeah.
Is there any reason you stick to just US Open and Wimbledon, not Australian Open and French Open?
Sorry?
Is there any reason why you just restricted the method just to the Wimbledon and US Open?
Oh, yeah. A very good question. So when I came to the internship last year, so the people from Wimbledon came to IBM to ask them to create a system. And this was right when I came into the team, so I worked into this with this problem. And later on, this problem was deployed for another, the second tournament, which is US Open. And so we have like more than 2 months to work on 2 different systems, which is one of the challenges.
More questions?
Yeah.
Where did you get the training sets for doing your classifications on action and facial expression? And how big were they?
Yeah, really good. So that is one of the challenge also. So for actually the facial expression is only officially done for the second tournament, the US Open. For the first one, we don't have that. And we didn't have any data at all. So we have to go online for the previous years of the tournaments to extract the players. And then we use them we have to actually eyeball all of them to annotate the results, and we train them.
More questions?
Yeah.
Is your combination just an aggregation of the 3 modalities that you're getting, or
Sorry?
like how exactly do you combine? Like you show it as a black box in terms of aggregation, but what exactly is
So for the visual information, to combine the celebration action and the facial expression, actually we can build a score called the emotion score, which is the weight difference between the emotional expression and non-emotional, which is neutral. And we use that to aggregate into our celebration action, and then we combine with the crowd sharing later on with some weighted summation.
Are there any other questions? No? Then thank you so much again.
Thanks.